Okay. Can you click on the Chem 101 link? Yeah, thank you. Okay, so this will launch right into Chem 101. If you go to the second tab where it says homework, click onto homework. You'll actually see your homework assignments. Veronica is already on top of it. So when you first log in, it's going to ask you information about you and your email address and all of those things. If you can use your school email address, that is the best email address to use when they do that, when you do that. And you can actually see your very first homework assignment other than getting started. Like I said, Veronica has already done the first one. The second one is already up. Okay, we'll be talking about what we're going to be going over today. So were you guys all clear on that? Not too hard? Okay. I need some type of confirmation. I understand that this is an online and you're not used to using Zoom or anything like that. You can unmute yourself to give me some type of confirmation that you guys are understanding what I'm saying, especially if you're not going to show your video, show yourselves. Then you need to let me know that you're doing okay. Thumbs up or something, okay? Are you guys clear?
Yes, clear. Everything is
good. Good.
Yeah.
Okay. So everybody here so far has already signed into Chem 101?
Yes.
Okay.
Yeah.
So if you guys look in the corner, see if I can do it. Let's see. You're already on top of it. You've already activated your the code, Veronica?
Yes.
You've already paid for it. See, Veronica's already on top of it. I need somebody who's just starting today, who's this is the first time that they're doing, and you haven't even got to this part yet. Anybody who's done that?
No, I started mine already.
See,
I paid for it.
I have the good people already. You know, this is good. That makes me feel good that you guys are already on top of things. Okay, it makes it easy. It makes this class be a lot easier if you guys are on top of it. Okay, because I know I've had a few people who've contacted me about logging on. Okay. Okay, so the next thing I'd like you to do, go back to the Chem class. So your very first tab. Go back to modules. Okay. Okay, so if you look there, let's see, resources. Under resources, at the very bottom, it says chemical packet. That basically has all of the items that are in the resources for you in one PDF. So you guys, you can see it off my screen. So I have like a conversion table, which we'll be talking about here in a couple of days. Another conversion table from the Army. And this one deals with pressure. So these are the common polyatomic ions. This is the activity series table. This is another activity series table. This is the solubility table. Okay, so all of these resources are available for you guys to use on your exams. Okay, so download this packet. I know it's going to cost you a little bit to print it out in color, but it's so much better in color because things are clear that way. Is there anybody who is colorblind? No. Good. Yes. No.
No.
No. Okay. Again, confirmation, thumbs up, thumbs down, you know, some type of confirmation. Let me know. Okay, so if you are colorblind, contact me. And if there's anything that you don't understand, because most of the things are labeled as well as using the colors, but it's a lot easier to see the colors. If you are colorblind, I will start trying to make other arrangements and also have a backup for you so that it's not reliant solely on the colors, which I have been doing anyway. Okay. Okay, so the other thing that I want to go over in modules. Let's see. if you go to the very first unit, the Crawless PPT, so that is your very first lecture notes. So go ahead and click on that. That is going to be your lecture notes. Thank you, Brittany. I wanted your signature. Okay, are you guys able to see that?
Yes.
Okay.
Yes.
So those are going to be the very first lecture notes. Those are the ones that we're going to be going over today. Okay. Hopefully we get through the whole thing. We'll do our best to try to get through as much of it as we possibly can. If not, we'll be picking it up, I guess, next week. Also, Fridays. I know you guys may not be able to make the labs on Fridays. It's okay if you don't make the labs on Fridays. And also, these lectures are for your benefit, right? So I recommend that you come to them because it's a lot easier to retain the information, but there will be there'll be recordings of the lectures posted. And then those recordings are going to be assignments to make sure that people are looking at the lectures, and there's going to be questions embedded in them. And so what I'll do is we'll go over the specific answers in this class. And so we should be going over it anyway. And so you want to make sure that you do that and then also go through and do the assignment, okay? So you don't have to look at the recording twice, but it doesn't hurt to look at it because it'll help you remember some of the items that we talked about in the class, okay? Are you guys good with that?
Yeah.
Okay, good.
Yes.
Okay, so Adriana, she says she's a little confused about the times of the lab. So my office hours are from 1:30 to 3:30. So this last week I was supposed to meet you guys at 1:30 to go over just the class and what's going on with the lab. Normally the lab is going to be from 3:30 to 6:30 on Fridays. So that's the only time that I could squeeze you guys in without having conflicts with meetings or other things. And then also my office hours, right? So if you can make that, that's great. Again, if you can't, don't worry about it. Just watch the video and everything is going to be self-paced. Do you guys know what I mean by self-paced?
Yes.
Anybody not know what I mean by self-paced? Okay, so just in case you don't know what it means, self-paced means that you're going to be going at your own pace. The key is to finish by the end of the semester. So there's a tendency of students to wait till the very end, that last week, to try to do everything. If you do that, I guarantee you that you will not pass the class, okay? So it's going to be set up so that you can complete each unit. So the first unit is going to be up by the end of the week. I'm going to have it completely up, all of the assignments and everything like that. The due date is going to be the very last day of class. That doesn't mean that you wait till the last day of class to do them. Okay, that's the same thing with the exams. The exams are going to be that very last, we'll say the last week of class, right? So that very last week of class, your exams are going to be due. Okay, and then at the very last week of class, so everything's going to be due, but you're not going to be able to go into the next unit until you complete that very first unit. You have to complete the first unit to get to the next unit, to get to the next unit. And I'm still, like I said, I'm still kind of new at this self-paced type of thing. Some of my colleagues have tried it and said it worked well for them and the students that were familiar with online classes. And I know that most of you guys signed up for this class because it was an online class and it fit into your schedule, right? And so since this is also self-paced, you're not required to come to the Zoom sessions. The Zoom sessions are for your benefit. You'll get it fresh, and then you can get started on your work and you can get started on the next thing, okay? So right now, things have dates. They will be changing so that they'll be due at the very end, right? That means there's no late work available or anything like that. So make sure that you guys are staying on top of that. Are there any questions on that?
No.
No.
I will be sending out the shopping list. I need to check the dates because I think obviously the dates that are on the Canvas shell are wrong because you've already missed it in that case. but I believe it'll be tomorrow. But I need to confirm that. I think it's tomorrow, Thursday, Friday, and Saturday that they'll have times available for you to pick up, and I'll provide the instructions on there. I will also send you an email stating exactly when you can do that. I will include that shopping list so you can go ahead and get that shopping list. All of the items are going to be it's going to be small. It's going to cost you about $20 total. So put aside 20 bucks. If you go to the stores that I tell you to go to, it'll cost you about 20 bucks or less. Okay. But if you go to, I don't know, some fancy store, then it could cost you something else, right? So, but if you go to like the 99, you guys have a 99-cent store in your area, and the Dollar Tree.
Yes, we do.
If you go to those, we'll get you hooked up for under 20 bucks, and it'll be everything that you're going to need for the semester. But you're also going to need to go to campus to pick up what they're providing you, because they're going to be giving you a scale and conical tubes. So I will actually give you the exact dates to that. I need to confirm those dates because I obviously have the wrong dates up there because I didn't have the current ones. So, but I'll be doing that as soon as I finish with this class, and it'll be posted as soon as I finish with this class. Okay. It would have been done earlier if I could have got the internet up and running. So, okay.
Do we need to pay for the lab equipment that they're going to give us
No.
at her now?
No, all you need to do is provide your student ID, and you're going to tell them CHEM22 in the section that you're in. You're going to hold up a sign, and literally you're just going to write that information on the sign, and they're going to come out and hand it to you. I believe that they have it. It'll be able to be picked up at the bus station on campus, on Hartnell's main campus. I'll have to look at the exact street because I don't remember off the top of my head. But I'll provide all of that information, and there'll be a link to it to also confirm, so that you can confirm directly from them as well too. Okay. If you happen to live hours and hours and hours away, if you give us your address, we will have the kit sent to you, right? And then I will give you the contact person to email to do that, because I'm not going to be the person that's sending it to you. It's going to be someone else. Okay. Any questions, any other questions? And I'll also state that in the email as well too, and the contact person that you'll be sending that to. Okay, so look for an email. You're going to be looking for a couple of emails from me today because there's a lot of things that you have to go over. Is there anybody here who is not registered in the class and is trying to get into it? Okay, good. So just out of curiosity, how many of you guys is this the first time that you guys are taking chemistry?
It's my first time.
Your very first time?
Mine
It's my
too.
first time too.
Okay. Are you guys nervous?
Very.
Yes.
Yes.
Well, that's a good sign. That means that you're taking it seriously. A little nerves is a healthy thing, So you guys get to see all my business here. Let me stop sharing. Yeah, so this class, if you stay on top of it, you're gonna be okay, right? And I kind of set it up, how many of you guys are really good at math? Anybody who's like, oh, math is my wheelhouse. I can do that like nobody's business. Anybody like that?
Nope, not me.
Okay. We're getting a lot of nopes on that one. Okay. I wish. Nope. I get to some degree. Okay. So if you're strong in math, you're going to kick butt. It's just like if you understand how it all works, you understood algebra, you went through it, no problem, you're going to do pretty well, but stay on top of it, because if you can get caught with your pants down. So you want to stay on top of it. Okay. If you're not strong in math, you can still do pretty well, but you're going to have to brush up on your algebra. And we'll be going over that, not this lecture, but mainly next lecture. There's going to be some memorization because you guys aren't familiar with everything. And so try to keep notes. What I always do is I'm going to share with you what I do to kind of get my notes set up. So when I download the lecture notes, then I'm going to go ahead and hit print. And I like everything in paper form. I don't know about you. doing things on the internet is not so much, or even a lot of you guys have tablets. You can use your tablets and write on your notes in tablets so that you have some record of it. So what I tend to do is I make instead of making a full page, I make it 3 slides, usually in color, so I can actually see the color. And can you guys see my screen right now? So I print out this, so then I'm able to take out notes on the side. So normally, if we were face-to-face, I'd print this out for you guys, you'd have it available. But unfortunately, since we're online, we're not doing that. There's a lot of money printing on my end, but a little bit of time. So, but I like paper, you know, I kill a lot of trees. And so then that way I always have my notes available and then I can go back and look at them. So make sure that you guys are taking notes to try to keep track of things as well. Okay. Okay, so let's go ahead and get started. Let's see. Okay, so can anybody tell me what is chemistry? What is the science of chemistry?
Math?
It's math? No, it's a little more than math, you know. We use math as a tool. Anybody else want to take a guess? What happens in a chemical reaction? Anybody? Bertha, what do you think happens in a chemical reaction? Oh, somebody said something. Reaction, yeah, that's right. Reaction. So what happens in the case of a chemical reaction? Okay, how many of you guys cook? Anybody cook? Did you guys cook breakfast this morning?
Not this morning, but I do cook.
You do cook? Okay, so, but you cook some mornings, right?
Right.
Okay, what do you typically cook? Do you cook eggs?
Eggs, bacon,
Okay, so let's talk about those eggs.
pancakes.
Okay, so if we look at that egg, right? We put it in the pan. Does it look the same way it does when we finish cooking it?
No.
No. What's happening then?
What is happening, it cooks and it turns different consistency, it turns different color. Once the yolk and I mean, it just looks different from when you
It looks
crack the
different,
egg. Right.
Okay, but you said some really crucial things. You made some observations, right? Would you say you made some observations there? Right?
Yes.
Okay, you said it changes color, it changes consistency, right? So
Right.
those are all signs of chemical reactions, right? So it's just the process of matter. Chemistry is just basically understanding matter, right? It's the aspect and the study of matter. That's what it boils down to. And then when we're looking at that egg is matter, right? It goes from one form to another form. That form, that change in form, is signs that there was a chemical reaction that occurred. And we'll talk about that here in a second, okay? But let's start with that matter. Okay, so everything has mass associated with it. From the smallest thing to the largest thing, everything has mass associated. Air has mass associated with it. So everything has mass that's going to be associated with it. So matter is going to consist of mass, okay? So things are going to have to, in our sense, weigh something, okay? So when we talk about matter, there's a couple of ways that we can describe matter, just observations that we make. So one of those ways is by using our eyes. So you can see a person, is that correct? You can tell that I have dreadlocks, right? Can you guys
Yes.
tell that by looking at me?
Yeah.
Yes.
And you
Yeah.
can see that with your eyes. You don't need a special tool to see that I have dreadlocks.
Correct.
Yeah.
Okay, so that is called macroscopic. Macro meaning big, scopic. So you're able to see it with your eyes. If you're able to see things with your eyes and able to make observations with your eyes, then it's going to be macroscopic. Okay. Microscopic is when we use a microscope. So what are some things that you're able to use a microscope to see? Or we need a microscope to see?
Need a
Bacteria?
microscope to see cells.
to see cells, like animal cells, plant cells, and somebody said, what, you said something else?
Bacteria.
Bacteria, yeah, bacteria cells, exactly. So we need microscopes to actually see those because, you know, we have bacteria on our skin, but can you see that little bacteria running around on your skin? No, we can't. Our eyes are not that good. If your eyes are that good, let me know. I have a job for you, so. Okay, that's microscopic. The fact that we're going to use a microscope, a normal type of microscope, a normal light microscope to sit there and see it, that means that it's going to be microscopic. So macro meaning big, micro meaning small. Okay, particulate. So particulate. So particulate is so small that you can't use a normal microscope to see it. You have to use a specialized microscope. Okay, so this gets in the realm of like molecules, atoms, viruses. So in that realm, so things that are so small that you need a specialized microscope to see it. Does that make sense?
Yes.
Yes.
Okay, so this first slide is just basically showing you all of that. And you want to be familiar with it. You want to be able to distinguish between that. So you may see a question like that on our little quiz. Okay, because things are so small, you know, I can't sit there and hold an atom in my hand because it's so tiny. So we need a way of representing those atoms. And the way that we do that in chemistry is that we often will use models. We have models of atoms, we have models of molecules. And so some of the common models that we use are like the ball and stick models. Why do you think it's called ball and stick? Bernice, why do you think it's called ball and stick? The ball and stick model. Or Angela, why do you think it's called the ball and stick model? Brandon?
Is it because it's a ball and a stick?
Thank you. It's because it's a ball and a stick. Yes. So sometimes chemistry is all about the obvious, right? So we use a ball and stick model because it's a ball and stick. So in this case, in the ball and stick model, the balls represents that atom. The sticks represents the bonds between the two atoms that we have, okay? So this allows us to do three-dimensional, like put the molecule in a three-dimensional space. So we can see somewhat what the molecule actually is going to look like. And then it kind of helps us understand how the molecule may be able to behave, okay? So if you take a look, okay, can you guys see my spotlight? So that's an example of the ball and stick model. And so here's another example of a ball and stick model. This is a plastic model that we've used for ball and stick. We also have another model that's commonly used. It's called the space filling model. So these are often used in computer renderings and stuff like that. Why do you think it's called space filling model? Don't be scared to talk. Paulina. Or Nada. Either you guys want to contribute? Brittany, since you're right on my screen, you should definitely want to contribute, right? Gabby? I'm gonna go through the whole list. Oops. Okay, so since you guys are gonna be difficult, work with me here. So it's called the space filling model because it fills up space, right? So if you take a look at it, it's basically, we have two colors here. This is also representing the same molecule. In this case, we're representing methane. The black ball represents carbon. The white ball represents hydrogen. Okay, so here in the space filling model, that gray, which is supposedly black, that's going to be your carbon. The white is going to be hydrogen. So methane, if we take a look at the chemical formula for methane, it's CH4. Okay. So it has 1 carbon and 4 hydrogens. Now, if you take a look how I wrote this, I know my handwriting is like a 3rd grader's at best, so you got to bear with me. So we have C, that means there's going to be 1 carbon. We don't put a 1 here. If it's understood to be a 1, we never put a 1 there, okay? This here represents the number of hydrogens we have. It's called a subscript. It's below the line next to that hydrogen. So it's CH4. Are you guys with me?
Yes.
Yes.
Okay, so let's see. How many of you guys are familiar with water? Do you guys drink water?
Yes.
Yes.
Good.
Yeah.
So what is the chemical formula for water?
H2O.
H2O.
H2.
I spill it all over my desk. H2O. H2O. Okay, again, you'll notice the H, it's a capital. The 2 is a subscript. So it's below the line and there's 2 hydrogens. So we have 2 hydrogens for 1 oxygen. So there's 2 hydrogens in water and it has 1 oxygen as well. Okay, are you with me?
Yes.
Yes.
Okay, so that brings us to the next part, right? So we've talked about that model. We have to use symbols, right? So we use that symbol, that H for hydrogen and that O for oxygen. So if you look on the periodic table, let's see. I'm used to having like 3 screens at once, so bear with me, 2 screens at least. Do you guys see my periodic table?
Yeah.
Okay.
Yeah.
So if we look at the periodic table, H stands for hydrogen, C stands for carbon, O stands for oxygen. What does Al stand for? Al,
Aluminum?
aluminum. Okay, now if we look at aluminum, it has 1 capital letter and then it has that L, right, which is lowercase. So
Right.
sometimes we have 2 letters, right? And sometimes we only have a single letter. If we have that single letter always has to be capital, like in the case of carbon, right? So for instance, if I have CO, what am I saying I have in this molecule?
You have 1 carbon and 1 oxygen.
That's correct. I'm saying I have 1 carbon and 1 oxygen. But if I write it like this, am I saying I have 1 carbon and 1 oxygen?
No.
Mhm.
No, what am I saying I have? What is CO? Do you guys see CO on my periodic table there?
Cobalt?
Cobalt. Yes. So this is saying that I have cobalt, where this is saying I have carbon, in this case, carbon monoxide, 1 carbon, 1 oxygen in that molecule. Okay, so they mean 2 totally different things. So we want to be aware of how we write things. So if I write it like this, 2 small c, a small c and a small o, that doesn't tell me anything, right? Because I need to make sure that it is capital, right? If I'm trying to say I have carbon and oxygen, they both need to be capital, right? And I can't just use a capital C and a small case O to stand for carbon and oxygen. I have to use capital C and a capital O. Does that make sense?
Yes,
Yeah.
makes sense.
Okay, good. Okay, so let's test out those skills. Now that means you guys have to interact with me. I know you guys are shy. There's no need to be shy.
It's
Let's try
that
this.
fear of being wrong.
It's okay to be wrong. You want to be wrong. It's okay to be wrong now. You don't want to be wrong on the test, right?
Right.
Okay, what about this? Okay, what is that top one? The top compound. It has what two elements in it?
Phosphorus and oxygen.
It has phosphorus and oxygen. That's correct. What about capital P, lowercase o?
Polonium.
Polonium, okay? Okay, so it's really important how we write it. We want to make sure that we're writing it correctly, because if we're not, it's going to cause problems and people aren't going to understand what we're talking about. So we always want to make sure that we're using capitals. We're supposed to use capitals, and lowercase when we're using lowercase. Because I will mark you off on that, definitely. Even though I think I know what you're talking about, I'm not going to give you that benefit of the doubt. You need to know what you're saying, okay? You need to write it down correctly, okay? So let's go back to the left. Okay, so are you guys familiar with the states of matter?
I'm not.
You're not? You've not heard of solid, liquid, and gas?
Oh, yes, I have.
Okay, so in the case of water, H2O. So in the case of water, we call the solid state of water what? What do we call it?
Ice.
So solid, it's ice. If it's a liquid,
Water.
okay, it's water. And if it's a gas,
Steam.
steam. Okay, so now I'm going to ask you a really hard question. You guys ready? Or vapor? Yes, vapor will work too. No, it's not air, because air is a mixture of everything. So it's either steam or vapor. Okay, water vapor. Okay, so here's my hard question. How do I get from ice to water?
With heat.
With heat. Ah, okay, okay. So, and then how do I get from water to vapor?
Temperature. Oh, for vapor.
More heat, that's right, temperature. So if we raise that temperature, what happens? We get more heat and we change the state. Do you guys understand?
Yes.
So we're able to go to those different states. Now I want you to sit there and think about it, okay? So if I have a bottle of water, right? And this bottle of water, I knock it over, which I just did earlier. Okay, so I knock it over. What's going to happen to the water? Is it going to stay in the bottle?
No.
It's going to spill.
It's going to spill. So does it move?
Yes.
Yes.
So it can move. Was that true?
Yes,
Yes.
it can move.
Okay. So if I have a bottle that was full, that was totally ice, and I knock it over, what's going to happen in that case?
It would stay in place because the ice.
Okay. So I'm going to ask you a hard question, and you may not know this or not. Do you think it moves? Do you think that ice is moving?
Yes.
Yes.
It just moves very slowly, correct?
That is correct. It just moves very, very slowly. That is correct. Okay. So, and we know that steam, what happens when we boil water? Have you guys you guys, I know you guys cook, right? You told me you cooked, right? So have you ever cooked the water out of the pot, not paying
Yes.
attention, right? Does it just stay above the pot?
Just
Or
stay
does
above,
or does it fill the entire room?
it fills up the entire room
It fills up the entire room. Why do you think it does that?
because it's moving at a faster pace. It's just
Yeah,
moving.
exactly. You're moving at a faster pace. So the way I like looking at this, I like to use this analogy, right? So we know that molecules are going to be moving, right? When it's ice, they're going to be moving really slowly. Have you guys ever been to a dance club that's really, really packed?
Yes.
Yes. See, I know one person has gone to the dance club. Like everybody else is like, well, I don't want to let them know that I'm out partying every weekend. And it's okay. You can party. We work hard. We play hard. That's okay. That's what we want, right? So
Right.
now when they're at the dance club and it's really, really packed, what happens? Can you move? Can you really get down there and do the curve, really get down and, get funky or anything like that? Or are you like doing really tight? You're doing a little head bend, because you don't have anywhere to go. Anyone there? Let me give you an example. Let me show you here. Let's see. Okay, now it's not working. Okay. Boy, me and my computer are having issues today. Can you see me? Let me pin myself.
Yes, we could see you.
Yeah.
Okay, so when you're in a nightclub and it's really packed, are you doing this? Or are you doing like all craziness? Which one are you doing?
The first one.
The first
The
one.
first one, because you're doing a little cute dance. You want to look cute but you don't want to sweat too much because there's so many people in there. You're all packed in. So you're just doing a little cute little dance in your head, going and everything like that, right? Now, in the case of water's kind of like a little different. You're able to get there and get your move on, right? You get a couple of steps in there, so you can move a little bit more, right? And then in the case of gas, you're like just bouncing off the wall. You have all the room in the world because you have all that space to fill up. Okay, so this here kind of represents what's happening in the case of molecules, right? So in the case of the solid, they're moving, but they're moving really slowly, right? In the case of the liquid, they're moving a little bit faster. In the case of the gas, they're bouncing off the walls and everything like that. So that process is called the kinetic molecular theory, right? Just the fact that things are moving and the fact that temperature causes this to happen. Have you ever been on a beach that the sand was really, 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 really hot? Yes,
Yes.
no, maybe?
Yes.
Yes.
Okay, now when the sand is really hot and you don't have your flip-flops on, are you, walking real cute to the water? Oh, girl, look at my
You're
bathing
running.
suit. Or you're running to the water. You're running, right? Because that temperature pushes it up. It pushes you up when you're on the sand to sit there and run to the water. It does the same thing to the molecules. It causes those molecules to move really fast, right? So that is all part of the kinetic molecular theory, okay? Okay, so kinetic molecular theory is just the fact that your molecules are moving, right? And they're gonna get that movement. The faster they move, the higher the temperature, right? If the temperature's slow, if the temperature's low, the slower they're gonna move, right? Then you can be cute, walk to the, to the sand. Okay, so we've talked about gas, we've talked about liquid, and we've talked about solids. So gases, those molecules are going to be moving fast. They're going to be further apart. They're going to occupy as much space as they can possibly occupy. Liquids are going to be contained in the volume, in the space that's given to them to occupy, right? And if we expand that space, they're going to try to occupy as much of it, but it's going to be limited to as far as that liquid can go. It's not going to be able to fill up the entire room if you only have a small glass of water, right? And a solid is going to be a fixed position, right? It's going to be kind of fixed, very limited in terms of its movement, okay? There are two types of solid. One is called a crystalline solid and one is called amorphous solid. A crystalline solid is organized. You guys seen crystals? You see how beautiful those crystals with their nice little points and everything like that? You guys seen that before, like on a crystal?
Yeah.
Okay, so those points are very organized. And so the molecules in there are very organized. They're not randomly dispersed or anything like that. It's really tightly organized. Where the amorphous solid, it's gonna lack order. So do you guys know what a morph is? Like morph, as anybody watch sci-fi movies? Morph.
No.
No sci-fiers here. Okay, morph basically means shape, right? So amorphous is like the lack of shape, so or the lack of order. So an amorphous solid is one that lacks order. It lacks that pattern that we see. Okay. Okay, so this is just a summary of all the things that we've talked about. We've talked about gas, how the molecules are moving everywhere and everything like that, and they'll just occupy the entire volume that they're able to sit there and occupy depending on the shape of the container. The particles are going to be moving fast, and they're going to be away from each other, and they're going to be almost independent of each other, randomly moving. So the liquid, on the other hand, it's going to have like a consistent volume. It's going to occupy like the cup of the glass, things like that. There's going to be some dependence on the molecules moving, right? So they're going to interact with each other in some cases. There can be some independence, but a lot of it is going to be dependent on each other, okay? And they're going to be kind of closer together than the case of the gas. And in the case of the solid is going to be, consistent, it's going to be rigid, it's going to be fixed. The volume is going to be consistent. It's going to vibrate in that fixed position. It's just going to move a little bit, very, very little. Okay, and you're going to get the particles that are going to be interacting with each other. And that interaction with each other is kind of what keeps that solid tightly fixed, right? It also kind of causes characteristics. So like, for instance, water. So if I put ice in water, does the ice sink to the bottom?
No.
No. Why do you think that's the case? Anyone?
Because it's heavier, maybe?
Because it's heavier? Ice is heavier than water?
Because the water's breaking down the ice, so it's floating above.
Okay, so those are all interesting thoughts. Well, I'll let you guys think about it. We'll give you a little more information, and then we'll ask the question again. But think about it. Put it in the back of your head as we talk about this. Okay. Okay, so this kind of leads us to what we're going to be talking about today. One of the major things we're talking about today, physical properties. Okay, so physical properties are characteristics that can be observed and measured without altering the identity of the substance. So if we go from water, which is H2O, to steam, which is H2O, we're not changing the chemical structure of that substance. It's exactly the same, right? So water and steam, chemically, they're both H2O, right? As we go from the liquid form to the gas form, they're still H2O. And if I freeze water to make ice, isn't ice still H2O? Okay, so yes, it's still H2O. So we're not changing the chemical structure of it at all. So that structure is exactly the same. So that would be a physical property or a physical change. The changing from liquid to a gas, that will be a physical change, okay? Now, a chemical change is where we actually change the identity of a substance. So for instance, we have sucrose. Sucrose is table sugar. Chemical formula for sucrose is C12H22 O11. this arrow represents yield. It means that we're making that. It means the reaction is going in that direction to make these products that we're going to get out of it. In this case, it makes carbon, just C, plus water. So if you look up top, I basically have wrote a chemical equation, right? Now this chemical equation isn't balanced, okay? But it represents chemical change. So we're going in a case where we have a molecule where you have carbon, 12 carbons, 22 hydrogens, and 11 oxygens all interacting together, okay? And then I'm breaking it down to carbon and water, okay? So this would represent a chemical reaction, okay? This is called a chemical change because we're taking these carbons and we're basically breaking them away from that molecule. So the carbons will be all by themselves. And then the water will be all by itself. Are you guys with me so far?
Yeah.
Okay. So yes. So I like trying to make caramels. I like trying to make candies and stuff like that every once in a while. It's that, I guess it's chemist in me. My problem is that I usually want to do it when I'm grading or when I've been drinking or something like that, when I'm not at the best of paying attention to things, okay? So like, for instance, the other night I was cooking up some caramels and stuff like that. I get some the table sugar started and everything like that. I get it started cooking and everything like that. And I like, you know, the caramels with the butter and a little bit of milk and everything like that. But you want to sit there and get your sugar start melting first, right? To get that brown caramel color to it. Then you add your butter to it and everything like that. So I put my sugar on and didn't pay attention to the temp at all. Put it on. By the time I finished, the next thing I know, the whole kitchen was all smoking, and then there was all this brown and black stuff just boiling all over the place and everything like that. So basically, I just did a chemical reaction. I put in so much energy that I was breaking some of the bonds between the sugar. And so when you break those bonds, you end up separating just the carbon and water. Okay, now I'm going to tell you a rule now, and I want you guys to remember this rule. Now it's going to pertain to a large percentage of chemistry, most of chemistry. This rule is, or it's actually a law. It's called the law of conservation. Are you guys with me?
Yes.
Yeah.
Yes.
And Maria, I'll get back to your thing about the cotton balls here in a second. Law of conservation. Okay, so the law of conservation of matter basically says what you put in, you must get out. Now, it can change forms, they can change partners and things like that, but what you put in, you must get out. Okay, so if you put it in there, it has to come out one way or the other. It's kind of like, do you guys eat? Everybody eat?
Yes, we eat.
Yeah. Can somebody help Samantha find the notes? Where would she find the notes for this section? Anybody want to tell her? You find them under modules. So if you go under modules, and it'll be under unit 1. Is unit 1 showing up for you guys?
Yes.
Okay. So under unit 1, it'll be chapter 2. Okay. It
So
says,
I
looks
found
like
it. Thank
you
you.
found it.
Yeah, I was looking under the wrong like unit.
Okay.
Sorry.
That's all right. That's all right. Well, it's good to ask because that's the way we find out things. Okay. Now back to the law of conservation. So, okay, so we have carbon. How many carbons do we have? We have 12, I should say. Let me kind of clarify. So on one side we have 12. So this side here is called the reactants. In this case, we only have a single reactant. The other side is called products. Okay, so we have reactants and products. Okay, on the reactant side, we have 12 carbon, you said? So we have 12 carbon. So I'm going to write it like this. On the product side, how many carbons do we have?
Just one.
How many do we see? We have 1. Okay. Now, I said what we put in, we must get out. Are we putting in exactly what we get out in this case? I put in 12 carbons. Am I getting out 12 carbons?
No.
No. Okay, so this is an example of an unbalanced chemical equation. So as chemists, we want to get a balanced chemical equation. And I'm going to show you how to go through that process of balancing your chemical equation. Okay. So, but first, let's write down how many of each thing that we have. Let's see, how many hydrogens do we have on the reactant side?
You got 22?
22.
We have 22. And then on the product side,
You have
2. That is
Two.
correct. 2. Yep, because that subscript is right next to that hydrogen. So that means we have 2 of those. Okay, what about oxygens?
you have 1?
On what side? The product side or the reactant side?
The product.
On the product, okay, so we have 1 on the product side and we have 11 on the reactant side. Okay, good job. Okay, so we know that this is imbalanced. So we need to try to find a way of balancing it out. So the way that we would balance it out is by using what we call coefficients. Coefficients are numbers that would go in front of that compound or that element or that atom. Okay, so if I want 12 carbons on my product side, what do I need to multiply 1 by to get 12?
12.
12. So what I'll do, I'll put 12 here, because that means that I multiply this by the number of carbons I have. 12 times 1 would be 12. So then that would be balanced. We have 12 carbons coming in and we have 12 carbons coming out. Does that make sense?
Yes.
Now, what about in the case of hydrogen? So what do I need to stick in front of this water molecule? And so the other thing about coefficient, it pertains to the whole molecule, right? So what we're changing is that whole molecule, okay? So that water molecule, how many water molecules must I have to make 2 or multiply? Say, what number of water molecules must I have to get 22 hydrogen?
11.
So if I have 2 there, what's this number be in front?
11.
11. Okay, so if I put 11 there, that gives me 22 hydrogens. And it also gives me 11 times 1.
1.
11 times 1 is 1?
11 times 1 is 11, sorry.
11, that's all right. 11 times 1 is 11. So we have 11 oxygens. So we know that this coefficient pertains to the whole molecule, right? So that tells me I have a total of 11 waters, right? 11 water molecules, okay? Here I have 12 carbon, okay? So, and this also lets me know that what I put in is what I got out. I had 11 oxygens coming in and I got 11 oxygens coming out. I had 22 hydrogens coming in. I have 22 hydrogens coming out. I have 12 carbons coming in, and I have 12 carbons coming out. Okay, so this is what the law of conservation kind of is for. What we put in, we have to get out. Now we can mix them up, we can break them apart, but at the end of the day, what you put in, you must get out. Does that make sense?
Yes.
So kind of like when you guys eat, right? So you eat food, what you put in your body, right? It either comes out, right? It comes out or you gain a little more weight, right? So you're accounting for everything that's coming in your body. It's either being pooped out as a product or it's making muscle mass or fat in my case, you know, a little extra pudge there, you know? You guys, are we clear on that? It makes sense?
Yes, it makes sense.
I have
Okay.
a question.
Yeah,
Those numbers that you added, the 12 and the 11, those have to be big numbers, right? Not little numbers like the
that's right. They have to
subscript?
be big numbers. Yes.
Okay.
So they're different than the subscripts. These are called your coefficients. Let me type that out so you guys remember that. So these are called your coefficients. They have to be big numbers and they pertain to that whole molecule or that whole atom that they're right next to. So in this case, this only pertains to this carbon. This 11 only pertains to the water. So it's the whole thing, not just the first thing. Okay, does that make sense?
Yeah, I
And
get
then,
that.
and then we often will put, there's a understood 1 here, right? So there's a 1 coefficient, but it's understood. So we never write that out. Okay, you guys think you can handle this?
Maybe.
Okay, let's see. We're going to go to a whiteboard. I'm going to put up an equation, an unbalanced chemical equation, and then I want you guys to work on balancing it. Okay, we'll start with this one. So this is methane gas reacting with oxygen gas is going to yield carbon dioxide and water. Okay, so what was the first thing that I did? Anyone? Remember, you want to be wrong now. You don't want to be wrong later, right? That's okay. Give it a shot. Anyone? Anybody want to take a guess? Okay, no volunteers. So who's going to get voluntold? Elizabeth, are you there?
Yes.
Okay, Elizabeth, what do you think the first thing I did was?
Write out all the elements.
Okay, I wrote out all of the elements. That's correct. So I have a C, I have an H, and I have an O. Okay. So help me out here. Anyone is able to. On the reactant side, which side is the reactant side? The left or the right?
The left.
The left.
Okay, so my reactant, I'm gonna write that up here. And then the other side is called what?
Product.
Products, that's right. Okay, so how many carbons do I have on my reactant side?
1.
And on my product side?
1.
How many hydrogens do I have on my reactant side?
4.
And on my product side?
2.
How many oxygens do I have on my reactant side?
2.
And on my product side?
1.
Okay. So, hard question. Is it balanced? Is what we put in what we got out?
No.
No. Okay, so what do we need to do to balance it? Okay, let's look. Look at our carbons. Are our carbons okay? We have 1 in and 1 out. Is that
Yeah.
good? Okay, carbons are good. So we're going to put a green check mark next to them. Okay, so those are good. Okay, now what about my hydrogens?
It's off by 2.
It's off by 2. So what do I need to do then? What can make it so I have 4 hydrogens?
Multiply.
Multiply by what?
By 2.
by 2. So I'm going to put a coefficient in front of my water molecule. So I have 2 times 2. Does that equal 4?
Yes.
Okay, so I have 4. Okay, so then that means now my hydrogens are looking good, right? Because 4 goes in and 4 goes out. Now what about my oxygens? How many oxygens do I have?
1.
I only have 1, so I have 1.
3 altogether.
Remember, it multiplies, right? So 2 times 1 is what?
2.
2, okay, plus, don't I have 1 here or 2 here?
It's 3.
How many total? There's 2 of these, right? The 2 is right next to the oxygen. So how many total do I have on the product side?
4.
4.
Okay, so I have 4. Okay, so I have 4 and I have 2 on the other side. So what do I need to do so that I would have 4 on my reactant side?
Multiply by 2.
Multiply by 2. So if I stick a 2 in front of here, that'll be 2 times 2. That's going to give me my 4. Okay, and then I can check off my oxygens. So I have 4 coming in, and then I have 4 going out. Does that make sense?
Yes.
Want to try one more?
Yeah.
Okay, let me add a page. Are there any questions so far, though, before we move to trying one more? Okay, good. I like it when there's no questions. Okay, so let's see. We'll do C3H8 plus O2 yields CO2 plus H2O. Okay. Okay, so first thing I'm going to do is to do what?
Separate the elements.
Okay, separate the elements. So I have a C, I have an H, and I have an O. Okay, so how many carbons do I have on my reactant side?
3.
And on my product side?
1.
Okay, how many hydrogens do I have on my reactant side?
8.
And on my product side?
2.
How many oxygens do I have on my reactant side?
2.
And on my product side?
1. Oh no. 3.
3, that's right, because I have 2 from the carbon dioxide and I have 1 from the water. Okay. Okay, is it balanced?
No.
No, it isn't balanced. Okay, so what do I need to do to balance it?
You'll have to multiply.
Okay, so where am I going to put the coefficient when I multiply? What am I going to multiply by?
The carbon by 3.
Okay, so I'm going to put a 3 in front of the carbon here on the product side.
Yes.
Okay. So I have a coefficient of 3 there. Okay, so then, what was that? So that would give me 3 carbons, 3 times 1. Okay, how many oxygens do I have now?
6,
Plus
7.
7. Okay, so my carbons are good. What about my hydrogens? Are they good?
No.
No. Okay, so what do I need to do to fix those hydrogens?
Put it E4.
Put a 4, okay, in front of the water.
Yeah.
Okay, so then that gives me 4 times 2. 4 times 2 is 8. Okay, so my hydrogens are good. What about my oxygens? How many do I have now?
Ten.
Okay, I have total of 10. So I have 3 times 2, that would be 6, plus 4 times 1. So that'll be a total of 10. So I have 10 oxygens. So but I only came in with 2. So how do I fix it? How many do I need to come in to balance that out?
You would multiply the other side by
Okay,
5 to make it 10.
5. Yep, that's right. 5 times 2, that equals 10. So that checks out, right? 10 going in, 10 coming out. Simple. Okay, good. So what I'm going to do is I'm going to give you guys, I'm going to give you 3, 4, I'm going to give you 4 problems. I'm going to put you guys in groups, and then I'm going to have you guys work them out. And then we'll come back and we'll work them out together. Is that cool?
Sure.
Okay. So let me, and talk with each other, you know, because these are your road dogs. They're going to help you get through this class. So don't be shy. And if you don't understand, talk to your classmates. They'll be able to try to help you out too, okay? Let's see. Okay, so let me give you your 4 equations. So your first one is going to be, okay. So I wrote up 4 equations. So what I'm going to have you guys do, if you guys go and to annotate, can you guys go to annotate? Do you see it? Okay, so if you go to annotate, you hit save, and then it'll say show in folder. You'll be able to find your folder with the annotation. Okay, was everybody able to do that? If you have a Chromebook, I don't think you can do it unless they've made an improvement. Okay, if not,
I'm sorry,
you can just
go
take
where?
if you go to annotate, so if you go to at the very top, it'll say you're viewing Dr. Henry's screen.
Yes.
If you click on there, it'll say there'll be three dots, or it'll say more, or it'll say options. So if you click on that, it'll say annotate.
Oh, yes, I see that.
Okay, and if you go to the end, you'll hit save, and it'll actually save a screenshot for you. Okay, or you could just take a screenshot with your cell phone. Okay, everybody's done that?
Yes.
Okay, so what I'm going to do now, I'm going to put you guys in a breakout room. And we're going to put you guys in groups of 4. 3 or 4. Okay, so I'm going to create the room. I'm going to say this should take you about, we'll say 15 minutes. I'll give you 18 minutes. 18 minutes, and then I'll have you guys come back. 15 minutes. 15 minutes is good. Okay, you guys ready? Okay, and I'm going to automatically move all you guys into your breakout rooms. Okay, the rooms are open. So should we start with the first one?
Yes.
Okay, so let's see, whiteboard. Oops. Oops. Okay, so what am I going to do for the very first one? Walk me through it.
Write down your elements
Okay.
on a row going down. So C.
Okay. Okay, I got my elements written down. Okay, so what's next?
You write down how many elements there are on each side.
Okay, so how many do I have on my product side?
5.
5 carbon. Okay, and the reactant side?
1.
Okay. Hydrogens on the product side
12.
and on the reactant side? I mean, sorry. I knew what you meant. You meant on the reactant side, but now on the product side?
2.
Okay. And oxygens on the reactant side
2.
and on the product side?
Is it 3?
That is correct.
Okay.
Okay, is it balanced?
No.
Okay, so what do I need to do to balance it?
A 5.
I'm going to put a 5. Where am I going to put a 5?
In front of C.
On the product side or the reactant side?
Rather.
Okay, right here. That is a funny 5. Hold on. Okay, 5. Okay, so then that means we have 5 carbons. How many oxygens do we have now?
11.
Okay, 11, because we have 5 times 2, that's 10 plus the 1. Okay, now what about the hydrogens?
You multiply by 6.
Multiply by 6. So I'm going to put in front of the H on the product side, or am I going to put it in front of the 1 on the reactant side?
On the product.
Okay, 6 here. Okay, so then that gives me how many hydrogens?
Well,
12. And how many oxygens?
it's 6 times 2, so 12 plus
12
mhm,
plus
plus
12
2.
plus 2.
Oh, yes, no, sorry. So 12 plus 10.
Okay, so then that gives me 22.
Correct.
Okay, So now I have 22 oxygens. So let's see, my carbon's checked out, my hydrogen's checked out. So what do I need to do with my oxygens?
You have to multiply it now on the reactant side.
Okay, by what?
Oh, by 11?
11. Okay,
But you only have 6 oxygen, right? Why
no, I
12?
have, oh, well, good question. I only had 6 oxygens. Yeah, she's right. So we didn't have 12, we had 6. So that'd be 16. So that's going to change our numbers on the other side. Good eye. Yeah, because 6 times 1. So that's 16. So this means that 16 here. So then how many, that's going to change this number here.
Now you multiply by 8.
Now we'll multiply by 8. Okay. Okay. So 8 times 2 is 16. That works out. Are we good?
Yes.
Okay, good. Okay, so that one is done. Let's do the next one. Okay, so where are we going to start?
By listing the elements.
Okay, we have Al, we have F, we have Ca, and we have N. Okay. Okay, how many aluminum do I have on my reactant side?
1,
Okay. And on my product side?
1,
Okay. How many fluorine do I have on my reactant side?
3,
And on my product side?
2,
How many calciums do I have on my reactant side?
3,
And on my product side?
1,
And how many nitrogens do I have on my reactant side?
2,
And on my product side?
1.
Okay. Okay, aluminum looks good. Okay, what about, fluorine? Is it balanced?
No.
Okay, so what do I need to do to make it balanced?
Do you add a 1 in front of the F or in front of fluorine
Okay, so on which side?
on the product side?
Okay, so if I put a 1 there, let's see. On the product side. So you're saying in front of the calcium fluoride? So here? Okay, so with that, change my numbers. Now I have 1 times 2. Is that what I wanted to do? Would that just give me my 2 that I had initially?
I think so.
Okay, so is that what I wanted to do?
Well, you
No,
definitely,
we want it to be 3.
So we want to put a 3 in front of there. Okay, so then let's go. Erase that, and then we'll put a 3. So 3 times 2. What is 3 times 2?
6.
6. Okay, now how can I make it so that my reactant side has the same amount? If there's 3 fluorines here, what do I need to put in front of that to multiply it by?
A2.
A 2. Okay, so then that means that we have 6 fluorines on both sides. What's in and what's out, that works out pretty well. But that changes my aluminum, doesn't it? Now this is no longer a valid. So how can I fix my aluminum? Now I have 2 on one side. And 1 on the other. How can I fix that?
Multiply by 2 on the aluminum side, on the yeah, on that side.
On the product side?
Okay.
Got it. Okay. So then that gives me, let's do the math. How many calciums do I have now? Aluminums, we have 2. How many calciums do I have?
3.
I have 3 on both sides. So 3 coming in and 3 going out. How many nitrogens do I have? On this side?
Is it 2?
It's 2, that's correct. Okay, so aluminums, 2 going in, 2 coming out. Fluorine, 6 going in, 6 coming out. Calciums, 3 coming in, 3 going out. Nitrogen, 2 coming in, 2 coming out. Is that balanced?
Yes.
Piece of cake? Chocolate
No.
with strawberry frosting?
Not really.
Right, it comes with time. You know, this is your first time doing it. You know, how many of you guys, I'm just curious, and maybe you guys are better than I was. How many of you guys came out of your parents running? First day you came out your mom, you're booking down the road. How many of you guys did that? No one? Okay,
That's definitely a no.
okay. So that's the same thing here. You're not expected to get it immediately, but work with it. It'll get better, you know? Okay, so let's do one more. Let's do the 2 more. Let's see. The next one is C6. H12. 06. Any of you guys have taken biology? No one? Well, you guys are so interactive. You guys, I just can't get you guys to shut up. You just keep talking and talking and talking. Anybody there? Or
I'm
did I
here,
lose
but
you?
I haven't taken the class yet.
Okay. Okay, well, this is an equation that you guys will see a lot in biology. I like that. Yes, I have, but I forgot most of it. Okay, so this is, have you guys heard of cellular respiration?
No.
Okay, cellular respiration is basically cells breathing. Okay, so why do you guys breathe? You know why you breathe?
To survive.
To survive. Okay, any other reason? So we can't survive without breathing, so we need it, right?
Oxygen into our body.
So we need to bring oxygen into our body. Yes. So part of breathing is the process of bringing oxygen in the body. Without oxygen, we're not able to digest food. We're not able to do much. So we need that oxygen because oxygen is part of the process of what we call cellular respiration. So if we take a look at this, O2 represents oxygen gas that we bring in. C6H12O6, that represents the simplest form of sugar. So like if we bring in sugar, like you eat that candy bar, that's going to be the simplest form of that candy bar, right? And then what do you breathe out? What do you guys breathe out?
CO2, carbon
CO2.
monoxide.
Carbon dioxide. So we breathe out carbon dioxide, and then a little bit later on, don't you got to go tinkle? After you eat or drink a meal or something like that, don't you have to go pee?
Yes.
Yes. So some of that pee is going to be the water that you're going to be pushing out as well. So we also produce water, right? So from sugar and oxygen, we're able to produce carbon dioxide and water. Also, we get what we call ATP. ATP is stands for adenosine triphosphate, and it's cellular energy. It stores energy that the cell needs to do things. Okay, and so it's a nice way of storing energy for later on is by using ATP, by generating ATP. So by us doing cellular respiration, we're able to generate, I think it's, I can't remember off the top of my head, it's anywhere from 32 to 36 ATP molecules, and from one piece of sugar, right, which is pretty good. Without a particular organelle, we would only be able to produce 2 ATP, right? So 236 is kind of a big deal. So this is a very big, important equation that you should know from biology and that you will need to know for biology. So you want to be very familiar with it. Now I'm going to ask you a really hard question. Is it balanced? Anybody say yes? It's balanced?
No, it's not balanced.
It's not balanced. Okay, so let's do that process. Let's do it if we get it done fast. So what are the first things that we do?
List the elements.
It's the elements. So we have C, H, and O. How many carbons do I have on my reactant side? This side.
6.
6. How many do I have on my product side?
1.
Okay. How many hydrogens do I have on my reactant side?
12.
And on my product side?
2.
2.
Oxygens on my reactant side?
8.
And on my product side?
3.
Okay. Is that balanced?
No.
Nope, it's not balanced. So what do I need to do?
Add a 3 in front of the C.
A 3 in front of the C. This C or the other C?
That one.
Okay, so then that would give me how many carbons?
6.
Are you sure? What's right next to that carbon? You see a number next to it?
No, so it's just 1.
Okay, so it's 1. So 1 times 3, that wouldn't be 6, right?
Okay, so I did 3 and then I multiplied it by the 2.
Yeah, so remember that 2 pertains to just that oxygen.
Oh, okay.
Yeah, so remember subscripts are going to pertain to what they're next to, right? What they're next to. Now, if that was in parentheses, right, and I had a parentheses here and a parentheses there, then it would pertain to both of them, okay? And I'll show you an example of that after this. Okay, so then how many carbons do I need?
6.
6.
I need to put a 6. Okay, so I need 6. Okay, so 6 times 1 would be
6.
okay, and then how many oxygens do I have?
2.
2 times 6?
Oh, 12.
12. So remember, the coefficient is going to be multiplied by everything that's in that chemical equation. So we have 6 times 2. So that's 12 plus,
Plus 1,
okay, so that's a total of how much?
13.
13. Okay. So are we balanced?
No.
No. Okay, so, but the carbons are checking off. So we'll go ahead and check those guys out. Okay, what about hydrogen? What do I need to do to get the hydrogens balanced?
Multiply it by 6.
Oh.
Sorry.
Multiply by 6.
Oh, that's okay.
So I'm going to put the 6 in front of the water.
Mhm.
Okay. Right there. Okay, so then that gives me how many hydrogens?
12.
Okay. And then how many oxygens total? So 6 times 2.
18.
I have 18 total. That's correct. So I have 6 times 1. So that would be 18. Okay. So is it balanced?
No.
Nope. It's not balanced. Okay, so what do I need to do to make it balanced? I know I have 6 here. These guys are good, so I don't want to put a number in front of here. So if I subtract my 6 from my 18, so 18 minus 6, how much is that?
12.
12. Okay. And what times 2 is going to equal 12?
6.
I'm going to put a 6 here. That'll give me the 12 that I need. So 12 plus 6, that's 18. So now I have a total of 18. Is that true? Yes, no, maybe?
That's right.
Okay. So nice way of remembering it is sugar is the devil. Sugar, which is C6H12O6, glucose, or you can say glucose is the devil. This is glucose. Is the devil 666? Make sense?
Yeah.
Okay. Gosh, no laughing at my bad jokes. God, you guys are a rough crowd. Okay, so let's do this last one. Now this one is a little tricky. Yeah. Oops. C2H6 plus O2 yields CO2 plus H2O. Okay. First thing, can you guys see my board, my whiteboard? It didn't freeze on you?
Yeah.
Okay, good. First thing I'm going to do is to do what?
List your element.
List my elements. Okay. So we have C, H, and an O. Okay. On my reactant side, how many carbons do I have?
2.
On my product side, how many carbons do I have?
1.
On my reactant side, how many hydrogens do I have?
6.
On my product side, how many hydrogens do I have?
2.
Okay. Now, what about my oxygens?
2.
And on my product side,
You have 2 and 3.
okay, so I have 2 plus 3, so that's, 3 altogether, right? 2 plus what? Yes. Okay, is it balanced?
No.
No, it's not balanced. Okay, so what do I need to do to balance it?
I put a 2 in front of the reactant site.
You put a 2 in front of where? The carbon?
Yeah.
Okay. So then that would give me 4. And then on my reactant side, I would have, on my product side, I would have how many? What do I need to do?
Oh, you put a 4 as well right there.
Okay. And then that gives me 4 times 2 is 8 plus 1. That gives me 9 oxygens. Okay. Is that good?
Yeah.
Okay, is it balanced?
No.
Okay, so what do I need to do next?
A 6 in front of the H2O.
Put a 6 in front of the H2O. So now I have 2 times 6 is 12. And then 2 times 6 is 12. Okay, so that looks good. Okay, how many oxygens do I have?
14.
4 times 2, that's 8. Plus 6 times 1. So that's 14. So I have 14 oxygens. So what do I need to put in front of the O2?
A 7.
Okay. Okay, piece of cake. So later on, I'll show you another way of doing this. Are there any questions? Okay, perfect. No questions, we can move forward.
Wait, so why is it 7 and 14?
Why is it 7 and 14? Oops, actually it's not. It's 2 times, it should be 14 here.
Oh, okay.
My bad. I forgot to multiply it by the 2. Good question. Yeah, that one was kind of hard. Yeah. I'm going to show you another way to do it. I think it's a little easier to remember than just kind of randomly put it there. The other thing that I want to say is if you take a look at the numbers, the 2, the 7, the 4, the 6, they can't be divided into each other, right? Because I can't divide 7 by 2 and get a whole number. So you want to make sure that you have the lowest common factor for all of them. Okay. Questions, concerns, Cash? Excellent. Okay, let's move forward. Okay, so we've talked about physical reactions and we've talked about chemical reactions. Now with chemical reactions, one way of thinking about it is, are you able to get back the element that you started out with, right? Like for instance, if we cook sugar, right, and we get coal and water, then can I put that coal back in to make sugar? Are you guys there? Okay, so let me see if I can explain this another way. Okay, so if you eat sugar, right, in the beginning, you eat sugar, how does that taste?
Sweet.
Sweet.
It tastes sweet. Now, if you eat coal, because basically if you have coal at the end, like you cook all of the sugar out of the thing just to have the carbon, that's coal. How does coal taste?
Cold.
Coal. Coal tastes like coal. So like charcoal, you guys know what I mean by charcoal, right? So carbon is just charcoal, right? So now they don't taste anything alike, right? Is there any way that I can get charcoal and make sugar? Can any of you guys do that? Now, if you can, let me know, because we can make millions and millions of dollars. Okay, so I can't get the charcoal to go back into sugar, right? So once it's coal, it's coal. Like once I burnt that sugar, it's done, right? Are you with me?
Yes.
Okay, good. So that's a sign of a chemical reaction. If you can't get back what you started with by just separation or anything like that, that means it's going to be a chemical reaction. Now, if I can get it back by like cooling it down or something like that, then it's a physical reaction, right? So like for instance, if I freeze ice, right, after ice melts, can I get ice back?
Yes.
Okay, so I'm going to ask you to test these skills, okay? Okay, so I have 3 reactions that are going on. I want you to tell me if it's a physical reaction or if it's a chemical reaction. Okay, the very first one, we have a log burning, okay? How many of you guys think that is a physical reaction? Is it a physical reaction or is it a chemical reaction? A log burning. Now, I want you guys to ask yourself, am I going to be able to get that log back if I burn it?
Oh,
If I can't get it back, then I know it's a chemical reaction, right? Okay, let's see, 8 out of 12. So there's 4 more people. Come on, you gotta vote. Three more people. Okay, everybody voted that wanted to vote. Those who didn't vote, gonna give you a hard time. Okay, so the correct answer is, what do you guys think it is?
chemical?
Chemical, yes, chemical reaction. So A is gonna be a chemical reaction because we're not able to get that log to come back after we burn it, right? We just get that ash. Okay, okay, the second one, B. Gotta relaunch this poll. Let's see. Okay, second one is a physical reaction or is it a chemical reaction? The second one is an icicle melting. Icicle melting. An icicle melting. Okay, so we got 9 out of 12 again. Okay, we're gonna go ahead and end the poll. Icicle melting. 10 out of 12. Oh, we got those last ones chiming in now. Icicle melting. Okay. So I'm gonna share my results with you guys. Can you guys see it? Can you guys see the results?
Yes, I could see it.
Yes.
Okay. So the correct answer is a physical reaction because we can collect all of the water that's dripping off and we can refreeze it and we'll get that icicle back, right? It may not be as pretty, but it will still get it back. Okay. So we're gonna launch one more, the last one, a glow stick. Okay, 10 out of 12 have voted. Share the results. The correct answer is a chemical reaction. So chemical reaction would be the correct answer. Questions? Concerns? Kool-Aid? Okay.
No.
I have a question,
Okay.
and I always wonder this. You know when you freeze Gatorade, like sometimes I leave it in the freezer and it just freezes, and then
Yes.
I get it out, and it just doesn't taste the same. Like it just won't taste the same.
Yes. Do you want to know why?
Yes, I do.
Okay. So there's one of the main reasons is because Gatorade is an example of a mixture. One of the things that we're going to be talking about. Okay. A mixture is things that can be separated. By you freezing it, you're freezing out the water and you're freezing out some of the other components of the mixtures, like the salts, right? And so they're separated from each other and they're not distributed evenly. So if you sit there and you shake it long enough, right after it all melted, it's going to taste very similar to the way it originally tasted. But if you don't, you're going to get that separation still in place.
Oh, so the key is to shake it.
Yes. Well, let it melt completely and then shake it.
Okay.
Because otherwise, you're not going to get a nice distribution.
Or put it in the blender.
Or yeah, or you can put it in a blender. Okay, let's see how we're doing on time. We're actually doing pretty good on time. So let's keep going. Let's see. Okay, so that brings us to our next topic. It's like I paid you to sit there and start talking about Gatorade. Look at that. Perfect. Our next topic is going to be talking about pure substances and mixtures. Okay, so a pure substance is one type of matter, and it only has that one type of matter. So if we're looking at sugar, sugar is a pure substance because it's all C6H12O6 or C12 H22O, C12 H22O20 O11, sorry. So in that case, they're all the same molecules. They're all the same things, right? There's no difference between them, okay? Now, a mixture is kind of like what we talked about with the Gatorade. The Gatorade is composed of sugar. It has that red dye. It has like potassium, I think it's carbonate or potassium carbonate in it. It has, so it's a mixture of multiple things in one solution. Does that make sense?
Yes.
Okay. So there are two types of mixtures, right? The two types of mixtures, we have what we call a homogeneous mixture. Let me type that out for you. Homogeneous. Homo means the same. Heterogeneous means different. So we have a homogeneous mixture and a heterogeneous mixture. Homogeneous means, or homogeneous means it looks the same. So visually, it looks the same. So if you make an observation, it looks exactly the same throughout the entire thing. Okay. Now, a heterogeneous mixture doesn't. So like, for instance, if I mixed okay, so as a kid, I used to go to the diner. I used to like going to Denny's. And so like my family was pretty poor. And so we went to restaurants and stuff only on special occasions, like if somebody got a new job or it's somebody's birthday or something like that. That was the only time that we'd ever go to restaurants. And so when we went to Denny's, it was like a big deal. So they used to have the sugar on the table in the jar that you can pour sugar into. And they'd also have the salt and pepper shakers at that time. They stopped doing it, I had noticed. And so what I used to do was I used to take the sugar and the salt, and I would take the salt and pour the salt all in the sugar and mix it all up. So, and then watch people as they put sugar in their coffee, right? So now you have salt and we have sugar, and we mix them together. So is that going to be a homogeneous mixture, or is that going to be a heterogeneous mixture? That's right, Samantha. It's going to be homogeneous because it looks exactly the same throughout the entire thing. Now I want you to think about this. So if I have salt and I have pepper and I mix them together, is that going to be a homogeneous mixture or a heterogeneous mixture? Again, that's right. It's going to be heterogeneous because we can tell the difference between salt and pepper, right? Are you guys with me? I know you're getting tired, like, oh God, is he gonna ever stop talking? Okay, one of the characteristics of mixtures is the fact that we're able to sit there and separate. We need to be able to separate them. But they also have what we call the physical properties that are going to be associated with that mixture. Now, how many of you guys cook? Anybody cook?
I cook.
Do you cook pasta?
Yes.
Okay, so you cook pasta, right? Why do you add salt to the water?
Because it brings the boiling point lower, right?
That's right. Okay, so it actually, what it does, it actually brings the boiling point up higher. So,
okay.
Yeah, so the thing is that the water gets hotter, so your pasta cooks faster, right? So you're not getting soggy noodles, right? So here's an example. This is just regular water. This is a solution of salt and water. And so we've changed our boiling point. The boiling point of water is 100 degrees Celsius. And if we put salt in it, the more salt we have, we increase our boiling point, right? So it won't boil until it's at a higher temperature, okay? And so by us having mixtures, we can affect how things are going to behave, the physical properties of that mixture, right? So water normally boils when it's totally pure. It boils at 100 degrees Celsius. And then when you add salt, it's going to increase that boil. Okay. So I want you guys to help me out with this. So if I have pure bromium in a bottle, right? So, and I have pure water, okay? Now, if I have the two here, I add them together, they form a mixture. Is that mixture homogeneous or heterogeneous?
Wouldn't it be homogeneous because it looks
Exactly
like
the same. That's right. So it would be homogeneous. And that would be in both cases, right? Now, pure bromine, is that homogeneous or is that heterogeneous? Or neither?
pure bromine would be homogeneous?
Actually, it's neither because it is a pure substance. It's only one thing. It's only bromine, right? So
Okay.
homogeneous, it was a trick question. I did it on purpose. Homogeneous refers to a mixture, right? It doesn't refer to pure substances. So when we're describing mixtures, we describe them as being homogeneous or heterogeneous. Okay, so this slide just basically told you everything that I just told you of the last two slides. Okay, Questions, concerns? Kool-Aid? Okay, so if I mixed pure alcohol and pure water together, is that going to give me a homogeneous solution or is that going to give me a heterogeneous solution?
Homogeneous.
Homogeneous.
It looks exactly the same, right? So if I have a mixture of iron and sulfur, is that homogeneous or heterogeneous?
Heterogeneous.
Heterogeneous, right? And so the thing about mixtures is that we're able to sit there and use the physical properties of those mixtures to sit there and separate it. So for instance, if I was trying to separate alcohol and water, then what I would do, I would use the boiling point, right? The fact that alcohol boils at like 89.6 degrees and where water boils at 100 degrees Celsius, right? So I could sit there and set it at a lower boiling point than in the case of water, and I'll be able to get the alcohol, get pure forms of the alcohol out. Does that make sense?
Yeah.
Yes.
Okay, so like in the case of sulfur and iron, because iron is magnetic, sulfur isn't. So if I run a magnet over the sulfur, over the sulfur and iron, I should be able to collect all of the sulfur. And if you guys do this, you could actually do the same experiment with cornflakes, because it's one of the high iron sugars. High iron cereals. So, okay, so means of separation. We can separate mixtures by using distillation. So that's like in the case of the alcohol and the water. So I could use the fact that one boils at a different boiling point than the other to rely on that separation factor. So that physical change, that physical component, okay? So the other way is filtration. Filtration is basically using, how many of you guys make coffee in the morning?
Every day.
Every morning? Yeah, I need my cup. I'm struggling today. I spilled half of it on my car. So, but when you guys make it, do you guys use the coffee filter? Or have you guys all moved to the Keurig?
Yeah, little pods.
Little pods. Everybody's in little pods now. But even in the case of the pods, they have this little filter in it, right? To keep the grinds out. So the grinds is collected in that filter, and the water just flows through. So then you're able to get the liquid without the grinds, right? Who wants grinds in their coffee? Anybody like grinds in their coffee? Yeah, right? So we're separating based upon the size of the particle. So if the filter size is correct, none of the grinds will go through that filter. We'll collect all the grinds up top, and then our coffee will be nice and clean and just that mixture of coffee and water, right? Without the grinds. Okay, so this is an example of a distillation column. And so again, what happens is that we're boiling our liquid here, and we're using the fact that one boils at a different point than the other. So what happens is that the one that boils earlier will get the water vapor, or the vapor, I shouldn't say water vapor, and it'll be able to flow through here. And then it flows through this tube where it's a cooling tube. So we have cool water coming in, and it runs down that tube to cool down that liquid. So then we'll get that pure liquid at the end. So in this case, they're just doing water. So we'll end up with pure water at the end. Okay. This is an example of gravitational filtration. So in this case of a filtration, we have a mixture that is a solid and a liquid, and then we'll sit there and pour it into our funnel that has filter paper in it. The filter paper will collect all of the solid particles, and the only thing that's going to be able to flow through is that liquid. Okay, so in the case of mixtures, we can separate mixtures on the fact of their physical properties. So we can use their boiling points, their melting points, their freezing points to sit there and separate them from other things. Now, element is like the purest of a substance. It can't be broken down into ordinary chemicals, right? That's the smallest part it can be broken down to is the element itself. Okay, Now, elements are going to have their own set of physical and chemical properties that allows them to be utilized in various ways. And so we'll be able to separate elements from each other. We have mixtures of elements, kind of like the sulfur and the iron. A compound is basically a pure substance that is composed of two or more different elements. Okay, so a compound is going to be something that is composed of two or more different elements that are bonded together. Okay. A molecule is composed of two or more elements. So not different elements, they can be different elements, but it's just two or more elements. Like for instance, we have O2. Well, O2 is a molecule, but O2 is not a compound, where CO2, that's a compound. And O2 is also what we call a diatomic element. So let me introduce you to the diatomic elements, and then I think that's where we're going to stop at, okay? So if we go to the periodic table, there are 7 diatomic elements. Okay, so your 7 diatomic elements are hydrogen, oxygen, hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Okay. Diatomic basically means they have 2 atoms, so it'll be H2 so it'll be H2 N2 F2 O2 I2 Cl2 and Br2. Another way of remembering it is have no fear of ice cold beer. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, bromine. Okay. Questions? Everybody tapped out? Okay, well, I will see you guys hopefully on Friday. If not, then hopefully you'll watch my video. I've been dying to say that all day. Okay, you guys have a good day. If there are no questions, if there are questions, ask them now or forever hold your peace. Any questions?
Where do you post recorded lectures?
Okay, your lectures, good question. The videos of the lectures are going to be posted under modules as well. If you go under modules, it'll say recorded lectures. And right there, that very first link is the very first lecture that we have. So where I was talking about the syllabus. And you'll hear me say what I always say, can you see my screen? Okay, so yeah, so you go ahead through these lectures. All of our lectures are going to be there. There are going to be some assignments associated with it. The very first one, you won't have assignments associated with that one, but you should go over what I talked about in the syllabus to make sure that you understand what's going on with this. Does that make sense? And usually it's going to take me about a day or two to get them up. So the lectures that we have today are the ones that I'm going to typically use, but I'm going to start putting lectures that I've used in the past. The stuff isn't going to pertain to them. So the timestamps and the due dates for things aren't going to pertain to those. Okay. So what you hear in those lectures are not going to be the same due date. So pay attention to the due dates on the assignments, which are all going to be at the very end of the semester. Okay. Does that make sense?
Yes.
Okay. So you will have recordings of my other lectures. They're going to be coming up there. And they're going to talk about assignments that don't pertain to you, just so you guys hear that. So just to be sure, so you guys know that they're not your assignments. And I'll try to remind you of that as well. Okay. Okay, so I did get some information. Your pickup for your labs, your lab material, it is the 9th, September 9th, 10th, 11th, and 13th. There'll be a link here. It's not active yet. I have to activate the link. It'll take you to the instructions on how to go to that pickup. If you cannot make it any of those days, you can have the material sent to you by mail, but you need to contact the one of the lab managers. And it's Tony, I believe it's CHEM. And so there'll be a link to his email at this link. Okay. And I'll also send you an email message reminding you of this link so you'll know exactly what you guys need to do. Okay.